Okay, I am told we are ready now. My name is Bryan Ulrich. I'm the chair of this session. And our first speaker is Dale Rucker. Dale's the Chief Technology Officer for Hydrogeophysics, and he's going to be talking today on the effects of haul roads on ore compaction and wettability of leach pads. Dale, for you.
Thanks a lot, Brian. We are running a little bit late, so I was told we have time for one question. I'm not sure why I got lucky enough to go first, but you can be guaranteed that's only going to be better from here. So I'm going to be talking about haul roads on leach pads, and as you can see from the picture, these haul roads can be quite wide, and that's rather compacted material compared to what you're going to be leaching. And so what we do is look at this phenomenon using electrical resistivity. So a general statement is that haulage and maintenance equipment traverse wide roads across leach pads, and there's usually two-way traffic, and these haul roads can be up to 30 meters or larger across. And you got cyclical and vibrational compaction of the ore, plus the wetting of the from water trucks, and that can significantly impact how the ore will respond to wetting during leaching, and also during drainage. And so we've investigated a number of these leach pads to determine the consequences of haulage using electrical resistivity imaging. Usually what we do is we come in and do the electrical resistivity, give the data to the client and walk away. So we don't have any ancillary information from drilling or compaction testing to verify what we have seen with the electrical resistivity, but we've done this a long time and we kind of know what to expect from our data. So just looking at general haulage networks across leach pads, I can go on Google Earth and look at that time function where you can go back in time and look at older aerial photos. And what I've done here is taken several leach pads across time and just drawn over top of them the main haulage roads in yellow. And what you can see is as they build up the leach pad through time, is that some of the larger roads will stay fixed, but the smaller ones will change their locations to accommodate construction and design. So you'll see here aerial photos from Google Earth. The top one is a gold mine with temporary roads from 2011 to 2016. The middle one is a gold mine with a permanent haulage road taken between 2011 and 2017. And the bottom is a copper mine with temporary roads between 2010 and 2018. Another look at some haul roads across gold mines. This is a little bit more detailed to show where the roads were placed going through time, 2012 through 2018. You can see that some of the major ones stay fixed through time, and some of the smaller ones move. And this is another gold mine here where you got one main haulage road over here on the west side. So in general, you look at how these roads are constructed. There's a typical road width, and it's this simple equation here where you got number of lanes and the actual truck width comes up with the final width. And if you just look at a schematic, this is pretty much how wide they would be, lane 1 and lane 2, with some half a width of a truck between them. And if we assume a CAT 797 with a width of 9.15 meters, the total 2-lane width of that road could be up to 32 meters wide. And then if we take additional assumptions where the ore density increases to about 2,000 kilograms per cubic meter, up to a depth of 15 meters, which includes several lifts, we can get an impacted tonnage of approximately 1 million metric tons per kilometer of haulage road. Or if you're looking at a 200 hectare leach pad, that's about 2%. So why are we underperforming by 2% on a leach pad? Well, haul roads could be one of your answers. So now we measure subsurface properties using electrical resistivity. Unfortunately, most earth materials can transmit electrical current. And I've put up a little chart here that shows the distribution of resistivity values, and our resistivity unit is ohm meters. And at the low end of the scale, where it's low resistivity or high conductivity, you get sulfides, and then moving into different types of rocks, there's clays, conglomerates, and then on the high end of resistivity, permafrost. So you could see several orders of magnitude and differences between different materials. And the rate of current flow is related to that material property, electrical resistivity or conductivity. And that electrical resistivity value can be influenced by a number of different parameters. Moisture is a big one. Consolidation, ionic strength of the pore water, which you think about raffinate and copper leaching, that's really high ionic strength. Temperature can also affect it. So all those things can add constructively or destructively to give you your final value. And this is how we make our measurements. We have a computer that controls the transmitter, which passes electrical current across metal objects in the ground. We use stainless steel stakes, and they're usually aligned at even intervals. We can use electrodes in boreholes. We can use just big pieces of metal. This is a well, for example. We pass electrical current and then measure, and the current is in the blue lines, and that sets up an electric field, which is the red lines. So then we measure the voltage, which is just the difference in the potential field. We put current in the ground, something that looks like this: positive polarity, negative polarity. And our voltage that we measure with our receiver has a similar shape. And then there are different arrangements of how we can put our electrodes in the ground and take our put a current in the ground and measure our voltage. And this is a little bit of schematic of how electrical current passes through porous media. It can go through the pores where they're interconnected with the amount of water, and if there's more water between the pores, then you get a more electrical current transfer. Or most soils and porous media have some sort of clay, so we can also get electrical current passing through the clay. So when we complete a survey, we usually lay out a bunch of electrodes, connect them with a multi-core cable, have a multi-channel resistivity meter to collect multiple voltage pairs simultaneously. Simple power supplies usually use a 12-volt battery, one or two of them. We've got that rectified waveform, make all of our data, and then we model it to obtain our resistivity distribution. So you can see, for example, across the leach pad, how many stainless steel stakes we may have out there, all this cabling, all this computer equipment. So it's no small endeavor. And it takes several hours to collect a line across a leach pad, but we can get several parallel lines in a day, and we can develop a big 3D model if we wanted to. So I'm going to show you some examples, 3 examples of electrical resistivity across several leach pads. So this first example is an 80-meter deep gold leach with permanent placed hull roads. The hull road location here shows high resistivity values to the liner. So we have a color contour scale here: low resistivity where it's usually wetter, high resistivity where it's drier, and then that liner at the bottom is an impermeable liner. And so water cannot pass through it and electrons cannot pass through it. So we see at the hull road location a split where the more conductive material is here, more conductive material is here. So all that material is not getting wetted. So if we, the historical document showed that a mean gold grade of 0.3 grams per ton with 75% recoverability. So if we look at the volume of the affected road, it is estimated that 27,000 ounces are trapped in the volume of material affected by the hull road. That's not a trivial amount. That's a lot of gold right there. In our second example, it's another gold leach pad. This one's ROM. It's roughly 60 meters deep. And across this, we have 2 types of roads. There's a hull road, and there's also light duty roads. We've got one hull road here that's quite wide, upwards to 75 meters. And this is a picture of the leach pad itself. And you can see here's a road. We got roads on the side. That's the liner in the back. So you can see impacts of these haul roads going quite deep into the leach pad where it's not allowing this material to be wetted. And this is an area of active leach where there is no haul road. So you can see a difference between this area and this area. So it's affecting how this material is draining. So the road was created shortly after construction began. We consider this a semi-permanent haul road and is unlikely to be removed in the future. The small haul road is estimated to have affected a mass of about 840,000 tons, estimated stacking grade of 0.6 grams per ton and 50% recoverability. That's 2,000 ounces. And the larger haul road, if we do the math, it's about 8,200 ounces. And in our last example, we see a copper leach pad with crushed ore, and that was placed on native bedrock. So that's commonly done in Arizona, the older ones. And so you can see the low resistivity material here in blue. The location of that historic haul road is right here. It's rather high resistivity, and they are doing active leaching, and you see that wet material setting on top of this buried haul road. The location of the haul road is highly resistive. It bisects two areas of leach pad with conductive material. Another thing that's interesting is that you don't see any of that wetted material getting into the native bedrock, which is a good sign. The haul road has rough dimensions of 70 meters wide, 50 meters height, extending for about 200 meters in length across the leach pad. So if we get the residual information about what that grade is, it's about acid soluble copper of 0.2%, which means nearly 2.8 million kilograms of copper lost to extraction from surface leaching. So in conclusions, haulage is a necessary part of the operations and management of the leach pad. However, their use can cause lower metal recovery due to reduced permeability. And with electrical resistivity geophysics, we can define that damage from the cause of permanent haul roads extending through the entire depth profile. Some of these temporary haul roads have shown to have long-term rip effects if they're not ripped properly. And we estimate about 2% of the metal can be lost from improperly ripped or from permanent haul roads. So if they can't be ripped adequately and you still want to go after that metal, then there's a couple things you can do. Both would require drilling. You can inject into them, or we've even seen this done where you put explosives into the leach pad and sort of increase the permeability by fluffing. So thanks very much. That's my talk. Hopefully I was quick enough to allow for some questions if you have any.
If there's any questions, if you'll go up to the microphone that's in the center, then people online can hear.
Dale, quick question. Does the haul road bisect how the flow of the solution, or it just depends?
So if you have natural gradients, so it would affect movement from up gradient to down gradient, or if you're just leaching from the whole thing just over top, you can see that it just doesn't get wet through that material. It won't flow through or from the top.
On these historic ones, do they do ripping as they go up, as they build it? If it's the all ramps or flat all roads, or have they done historic ripping, or is it just over the top?
Yes. So they'll have a ripper. It's either 3 or 6 feet in length and go through. But sometimes the damage is a little bit deeper, or maybe it just doesn't get done or doesn't get done adequately. So there can be, ineffective management. All right. Well, yeah. Thank you.
Thanks. Thanks, Dale. And if anybody came in late and they're confused why Dale was still talking, we had some IT issues. Our last speakers dropped out, so all the talks are shifted by 20 minutes. So if you tried to miss Dale's talk, sorry, you got a surprise talk there. Our next speaker is Larry Bolton. He's a senior instrumentation sales representative from Emerson Automation Solutions. And just waiting for your slides to come up. Larry's going to be talking about wireless heap leach monitoring and control.
All right. Good morning, everyone. Thank you for having me. I appreciate it. Again, I'm Larry Bolton with Emerson Automation Solutions. I call on all the mines in Arizona and southwestern New Mexico. So today, you're going to talk about some of the successes we've had. If you have questions, you don't have to wait till the end, but ready to go. See if this works. Come on. There we go. So my partner in crime, Sherry Hurley, couldn't be here, but Emerson works with local business partners, what we call impact partners. And in this case, it's Caltrol. So I do instrumentation. They do some of the engineering. We work together on solutions. Just depends upon how things work out for us. But I've been doing working with Emerson for 21 years. And before that, I was with another automation supplier for 14. So got a little bit of knowledge, which makes me dangerous. So obviously everybody knows heap leaching, but basically what I intend to do is go through heap leaching, the wireless instrumentation we have, the efficient operations that we've seen, safety, health, and lastly, environment, which are very key to why people need to implement this. So in a nutshell, heap leaching, I'm familiar with copper for the most part. And so I won't belabor this point, but essentially what we're measuring is the distribution on the pad itself. Obviously, there's instrumentation that'll measure what's coming to the pad, what's coming out of the pad, but what's been lacking is instrumentation that you could place on the pad, show the distribution, get the right flows in the areas you need it, more if it's got material that consumes, in this case, the acid, the raffinate, or less if you see ponding or something else going on. There we go. So just kind of a quick overview of the technology. So first of all, what's our network? It's wireless HART, which is an open protocol, operates on the 2.4 gigahertz band. So it's got built-in security, 5 levels of security, including frequency hopping, key network key ID and join keys, as well as encryption and a couple other things to make sure you have a secure network, one that can't be hacked, one that can't be spoofed. And then basically what we try and do, if I can use this. So it's about a 10 milliwatt signal. So what's important is the network, not necessarily the individual devices, although you have to make sure that they have access and visibility to other instrumentation. Each of the devices will receive and retransmit, if necessary, the gateway up here. The gateway is what will determine how that signal gets from the individual device out to back to the gateway, and then from there it'll get into your control system, whether you're sending that through to Pi or another historian. So with Emerson is one of these large companies with lots of instrumentation, control systems, valves, you name it, we've got it. How we go to market is a little different. That's why we partner with Caltrol quite a bit. But with our control system, we have Delta V, and that will take in a wireless input natively. You can also, via the gateway, bring it in OPC, Modbus, RTU, Ethernet IP. So many ways of getting that wireless data from our devices to the gateway and then from the gateway into your system. Very easy to actually do. My expertise is actually on the wireless end of it, not necessarily hooking up to the from there. That's where Caltro would come in and they'd help set that up if necessary. So let me start with what we're doing first of all. It's measuring pressure and flow of the lines. This one device, the 3051 SMV, is the device that'll measure both. Hard to see on that cutaway, but there is a differential pressure sensor in there that'll measure the differential and then calculate the flow rate based upon that. And also buried in here is a static pressure sensor, and that'll tell you the pressure of what's going out. So between those two things, you'll get your two process variables. There's other process variables that we send out, including your power module or battery strength. We also send out a health. Is this process variable? Is it stale? Is it active? So things that we can do to help make sure that you have a pad that is getting back real information real time. And also that the data you're collecting is good. In general, you can set these up to transmit anywhere from 1 second to 60 minutes. However, on a leach pad where we're trying to cover long distances, we usually do about a 1 minute update rate. But if you think about it, normally you had no measurements up there. Now you're going to a 1 minute update rate. That's a lot of data that you didn't have before that you're going to be crunching. And the other thing is that then you need to figure out, okay, how do we monitor this? And the big thing is you're going to be looking at the trending of the data. How is that going? Are our flows getting out there that we need? Do we have a broken line? What have you? So the other nice thing about this device is this is what we call our super module. So basically the electronics, if you will, are buried in that. It's hermetically sealed. It's all 316 stainless steel. And then the only thing up in the housing is going to be your display. If you have an LCD display, your radio card is in there, and then your antenna. So, and then the battery plugs into the backside. So basically it's a device then that all in one. You don't have to have any solar panels. You don't have to have any inverters or lead acid batteries or anything like that. So it's a very compact, very robust device. The power modules are lithium and they are not rechargeable, but we do estimate on a 1 minute update rate, depending upon the temperature and what have you, you should get about 5 to 10 years out of each module, in which case you would replace it. So there's a few other parameters in there, which I'm not going to go into the detail, but I'm happy to answer your questions later. So the other thing that makes this possible is our 405C conditioning orifice plate. And this is something that Emerson developed, patented. And what that allows us to do is get the same accuracy on a orifice plate in 2 pipe diameters, where a standard orifice plate may require 40 pipe diameters upstream and downstream to get you the same accuracy. So this gets you the accuracy you need in a single device. And as you can see, this is how we can sell it. That goes up to about a 12-inch line size. If you need a bigger one, we have a separate plate. But this is a nice, convenient way of getting all in one and getting that information out. So basically the 4 holes just does a conditioning. On the downstream side, on the upstream side is where you're going to get your pressure measurement. So between those two coming out, then you've got the 2 bits of data you need. Come on. There we go. One of the other things that we have developed is our 702 discrete transmitter. And what that allows us to do is remotely switch. So it's got 2 discrete switches inside, and we can use that to do one of two things, either act as a repeater where we're not even using the switches, or actually use those switches to activate flush valves. So oftentimes you'll need to flush daily, every other day, something like that. You can do this remotely if that's allowed. And then your information on your flow will also indicate that, hey, the flush worked. We could see that it happened, and then shut it down and you'll know that it's actually closed. So you got that feedback loop going on. So that's important to keep your lines clear. The 702 comes with different antennas. So you can see that antenna is one of our big ones, and that'll get, depending, about half a kilometer or a kilometer. We also have other styles. Depends upon your application, how we're going to get that signal out. And that's something that we would walk you through. So one of the things that this has allowed us to do is improve the efficiency on leach pads. So you're not pumping raffinate or solution into areas that don't need it. You can route it around. You can see that you've got the side slope. Make sure you're not sucking a lot of your solution and it's being wasted here and it's not being distributed up there. You can make sure that what's going on out here, so your water balancers aren't chasing their tails, adjusting flows here, then they adjust flows there, and then by the time they're at the end, they got to go all the way back to the beginning again and do that all over. So that's one of the key things, is keeping things efficient. So this is just kind of goes into some of the other efficiencies that we can do. So obviously you've got, your pump that we have here. We can do vibration monitoring, temperature monitoring, lube monitoring. And then from that, we have the distribution up here. We can also measure the temperature down in the hole. We are developing, this is our beta unit for developing a downhole probe for measuring the pressure inside. So kind of our path has been, you start here, we've gone here, now we're going in here. So basically this is no longer a black box where you don't know what's going on inside. So that's kind of a path that we've developed. So we're trying to improve your control, trying to improve the safety, the efficiency, and your environmental stewardship. And where that's important, let me back up a little bit. So we have a couple of software packages that then will help you maintain and monitor your network health, as well as your power module management, so that you don't have units that have dropped out, and you can always follow along and what's going on. The network manager is pretty interesting because it'll allow you on your cell phone or laptop, what have you, to see where you have issues, where maybe a device has become isolated for whatever reason. And then you can actually then drill down and see what's the issue. Is it lost connection? Is it maybe isolated to where it's only has one path out? So there's a lot of tools we can use to get you the information you need to monitor and manage it. So the safety and health, and this is kind of a no-brainer really, is if you know what's going on up here, do you have a broken line where you could have liquefaction, you could have erosion, things, a line is broken and is starting to wash away and maybe getting into national waters. That's going to be key to preventing getting large fines and having maybe issues with the local population. So this is something that we're pretty proud of, that it improves your safety and health. You're now looking at what's going on your pads 24/7, where before you only had daylight hours basically to work and monitor what's going on. And you can see whether it's monitoring what's going on a header, or what's going on up here. Whether you're talking about drip lines or wobblers or sprinklers, we can handle it all. This is an epoxy painted housing, so it's not getting hit with acid. However, we do stainless steel as well. Couple of other things we can do if you got like high chlorides or something like that, we can we've got some different materials we can utilize. So again, this is the environmental stewardship where you're trying to make sure that you're not having liquefaction on your pad. So again, if you know where the material is going, you know what's going on inside it, then you can prevent ponding inside your pads. You can prevent side slopes from sloughing away. Basically helps prevent fines from governments. So that's about it. Any questions? Cool. Thank you.
All right, we are a couple minutes ahead of schedule. So our next talk is Jason Keller. He's a senior hydrologist from Geosystems Analysis Incorporated. And he will be speaking on ore permeability and blending evaluation to optimize leach performance, which kind of goes hand in hand with this morning's keynote talk. And with that, welcome.
All right. Thank you all for attending the talk here. Start off by recognizing my co-authors with this talk, Zhongmao Yao and Mike Nazarek with Geosystems Analysis, and Vince Loftus and Stuart Mearhow with Round Mountain Gold Corporation. So this talk will be talking about some heap leach characterization work that was done at Round Mountain Mine. Specifically, this was done on their Gold Hill deposit, which is a satellite deposit just north of the main Gold Hill. Many of you here may be familiar with the location around Mountain Mine. It's located in south central Nevada. It's a conventional open pit mining methods are done there, most with ore dump, leaching, run of mine, ore. And to mention, 2011, they expanded into the Gold Hill deposit, which is a quartz alveolar low sulfidation hydrothermal deposit. That always gets me as a hydrogeologist. That whole string right there is a tough one for me to get out of my mouth. It's hosted in volcanic ashfall tuffs, and the upper portion of the deposit is oxidized, so it makes it highly amenable to cyanide heap leaching. So in preparation of the expansion into the Gold Hill deposit, they had done some feasibility testing as is typical. And during that time, there was no issues in terms of percolation issues. But then immediately after stacking their first lift and beginning to operate out there, they identified ponding on the surface, which the photo here is showing. That's a picture of the leach pad, and on the surface you can see ponding. So what they then did is they reduced their lift heights from what was 50 feet down to 25 feet in hope that would reduce the consolidation and increase the permeability. And at the same time, they reduced their application rate from 0.003 gallons per minute foot square to 0.015, which of course that's not ideal, because then that reduced their mining rate by about 1/2. So the effects, as I just mentioned, this had a big impact on their gold production. And then looking with the surface ponding, the low percolation rates, and also doing some work to look at the ore water solution content. It was near saturation or high water content. So they quickly identified that, all right, there's poor permeability here. That's the issue. And so they they moved forward with doing a characterization program to understand the hydrodynamics of the ore material that they're mining, and also mitigation strategies that they could use to increase the ore permeability. Oh, the plot here I'll also call out is just want to show we have the time from 2012 to 2014 and what the ore that's placed, the gold ounces that were placed, and then what was budgeted to be produced, the blue line, and then the red line indicates what was actually produced there. So just to give an indication of where they were underperforming in terms of their gold recovery. So this hydrodynamic testing program, it included three ore types, ROM ore types from the pit. There was the siliceous potassic, which is the picture shown on the top. It's a coarser ore material, an argillic ore, which is on the bottom left, and then advanced argillic ore, so a highly weathered ore. And the testing program consisted of consolidation permeability, so performing saturated hydraulic conductivity measurements under load, which would replicate depths within the leach, within the heat pad. Particle size distribution to understand what the gravel and fine content is in there. And then clay speciation, looking at XRD analysis. So is there swelling type clays in there? There were some other physical property measurements we performed, particles or specific gravity, some Atterberg measurements and so forth, but we don't go into that here. I won't go into that in this presentation. So the consolidation permeability testing, just to go in a little bit more detail about what that test is. It's a dual wall test, flexible wall cell that's packed either typically we use 6 inches or 12-inch diameter cell that 12 inches long. It just really depends on the particle size distribution, how coarse the particles are, and the largest particle size. And what we do is we then allow us to test a variable densities, bulk densities, or variable consolidation. So what that allows us to do then is understand the saturated hydraulic conductivity of the ore under different heap heights or depth in the heat. The other thing about using this dual wall flex wall system is one, it minimizes the potential for edge effects, so preferential flow of solution in your measurement cell along the wall, which tends to happen especially if you have coarse particles, gravels, that they don't seal up against the wall. So by having that flex wall, it pushes it in and reduces the potential for edge effects. And then in addition, having that wall flex wall, it provides a more consistent compression around the entire column. And so you have more uniform consolidation within that cell versus, say, just a uniaxial, one-dimensional uniaxial compression vertically from the top. So that's the benefit of doing that flex wall cell. And I'll show some pictures here coming up of what that looks like. So with this setup, the flex wall, you can also do unsaturated hydraulic conductivity measurements, essentially irrigating on the top of the cell, at a particular rate, and then you can consolidate to look at what the solution content would be in that material under different flow rates at particular depths in the heap leach pad. So in terms of this analysis, we established some criteria to look at in this ore. One is that the saturated hydraulic conductivity is 100 times greater than the forecasting irrigation rate there, which is 0.003 GPM per foot squared. Now, the 100x factor, why that's applied, is to account for just variability in the ore material. I mean, we have these samples, but they're just grab samples. So accounting for that, accounting for variability in the emitters, the irrigation lines, if it's not always perfect across the entire surface of the pad, accounting for precipitation, accounting for uneven surface on the pad. So it's really to account for all these unknowns that we really we don't know. And so we apply a 100x safety factor here. What we're looking at is also in terms of favorable criteria is we want to see minimal or not minimal, but less ore consolidation with depth. We don't want to see a bulk density increase significantly with consolidation. And then again, absence of swelling clays. I mentioned we don't want to see the swelling clays because that can a small amount of swelling clay in the sample can greatly impact the permeability of that material. So here's just an example of a flex wall cell where on the left, we consolidated it to what would be equivalent to 10 feet below the surface. On the right is equivalent to 30 feet below ground surface. What we did is after doing the consolidation and the work, we then froze the cell and extruded it so that it looks like this. So you can see with the 10 foot on the left, you can see some pore network which you would expect to translate into higher permeability conditions. And or on the right, which is again 30 feet, you see a reduced pore network visually, and so reduce permeability of that ore material would be expected. So this is just an example of the cell. What it looks like on the left is a 6-inch diameter column. That's actually undergoing unsaturated hydraulic tests. There's emitters, drippers here on the surface that's dripping onto the surface at a particular rate, and we're monitoring the solution content and the matrix potential within the column. On the right is a 12-inch diameter flex wall column that's undergoing saturated hydraulic conductivity measurement. So you can see it's a fairly large column, and all the test work that I'm presenting here was done in a 12-inch diameter column. There we go. This is an example of just looking at the top of column after a test was performed. This is a coarser textured ores. You can see, just to get an idea, you can see the rubber membrane around the end, around the edge. That's the flex wall component of the cell. And then the next slide will be a finer textured sample there where that was done. The test work was done afterwards. The pressure was released of the cell. So that's why there's a gap in the headspace there, because the pressure was released. And so the material settled back down. And just a final picture here coming up of a 6-inch diameter cell. There we go. So let's move into the results of this characterization study that was performed. So first, the particle size distribution. Now, I mentioned there's three. Every ore type was done. There was 3 samples, so done in triplicate. And so what we see here for the particle size distribution is the average of those 3. Just a couple things to point out here is let's look at the gravel and the silt and clay. So the SP ore, it was had much more gravel size material and about 8% silt and clay, whereas the argillic ore had less gravel size material, about a similar, a little bit more silt and clay, but more sand material on that one. And then the advanced argillic, you can see very much less clay than the other 2 material types, and much greater silt and clay. One thing to bring up is this PSD indicator, the last column here. The PSD indicator is the percent gravel, so the percent greater than 4.75 millimeter, divided by the percent passing the 100 mesh. And I bring this up because this will come up in a few slides later when we did correlation analysis to identify a relationship between measured hydraulic conductivity or permeability and some physical parameter. And so what that really conceptually what that is the gravel particles, the gravel size particles, that supports macropore flow, macropore solution flow, whereas the percent passing the 100 mesh, that's more the finer particles. That's going to be what's associated with micropore flow, but also that's going to also be most relevant to consolidation of the material. The finer textured material will undergo or really be undergo the consolidation. The clay speciation. So what we identified here, again, this XRD analysis, is both the SP and the argillic ores had very little smectite. So smectite is swelling type clay. We see 2% or less for those ores. However, the advanced argillic, we do see upwards to 8% of smectite type clay in one of those samples and 4% in another. So there is swelling type clays in here. So not only is it a finer textured ore, but it also has swelling type clays associated with it. All right, now the consolidation permeability results. There's a lot going on here, and the next slide summarizes it in table, but we'll step through this here so you can get an idea of what the results look like and how we evaluate those results. On the y-axis is the estimated heap height or depth within the heap, going from 0 to just over 80 feet. That's our measurement range of what we're looking at for consolidation. Along the y-axis, the x-axis is the saturated hydraulic conductivity, which actually decreasing from left to right. Now, as you are in the white range of that graph, that's above that 100x safety factor. The hydraulic conductivity is above the 100x times the irrigation rate, the target irrigation rate. When you get into the yellow box, you're now below that 100x factor. You're above the target irrigation rate of 0.003 GPM per foot square, but you're now below the 100x safety factor. And when you're within the red box, now at that point you are below the forecasting irrigation rate. So what we see here is the SP ore, the coarser textured ores, which are the red colored here. They all with depth, we see very little change in saturated hydraulic conductivity with depth. They all remain in that white area, so above the 100x safety factor. The argillic ores, which are the more green colored ores here, we see that they do decrease by 1 to 1.5 orders of magnitude over our range of measurement. And eventually anywhere, depending on which argillic sample we were looking at, around 40 feet to 60 feet below ground surface, it drops below the 100x safety factor. Whereas the advanced argillic ores, which is a little harder with the color because of the cells, but they are essentially near or below the 100x safety factor at the surface, and then drop, and 2 of those samples drop below the forecasting irrigation rate at a depth of around 20 feet. Now, what we also looked at is blending. So blending was something of interest because of course, they have this ore, they need to do something with it, and it's their target ore. However, within their mining plan, I mean, ideally, they would be able to blend with the SP ore because it's coarser, but there just wasn't a whole lot of that ore. And so they knew if they were going to blend, they were going to have to blend with the argillic and advanced argillic. So we looked at blending that the same rate, 75% to 25%. However, we just blended with some of the different triplicate samples. And this, for the dashed line, is those blending results. And with this particular sample here, it did remain above the 100x safety factor until about 60 feet below ground, below the heap surface, whereas the others drop below that. So just to summarize what I just showed you in a table, this is showing the sample, the 100x irrigation forecasting irrigation rate, and then the forecasting irrigation rate. So where it's green highlighted, that's positive, that's great. Yellow is marginal performance in terms of permeability, and then red is it really fails at what we'd like to see. So again, the SP ores looks good, so should not have percolation issues under. They're still doing 25-foot lifts here, so under the 3 lift conditions, it should be fine. Which I should mention, maybe to head this question off now, is our test work, we do focus down to about 80 feet below ground surface, between 70 to 80 feet below ground, below the heap surface. The reason being is that in terms of your gold or copper recovery, that's really where those first few lifts is really where you should be getting the majority of recovery of the recoverable metal. So below that point, we don't focus as much on. We're really just looking at those first 2 to 3 lifts, first 1, 2, and 3 lifts, because that's ideally where you're getting most of your recovery. The argillic ore, so they had exceeded the 100x safety factor, again anywhere from 40 to about 60 feet below the heap surface, and then the advanced argillic, really it just at all lifts, potential lifts, it would likely fail. So what we're seeing with the argillic ores is maybe under 2 maybe 3 lift height conditions, it should be sufficiently permeable. And then I mentioned this one blend sample where it was performed marginally well, so indicated there is potential to blend this ore and still be able to have sufficient permeability under a couple lift conditions, 2 to 3 lifts. All right, I had mentioned the correlation analysis. So something else that we did with this is we have the hydraulic conductivity measurements we performed, and we wanted to look at correlating that to fairly easy to measure, low cost physical measurements. So we looked at the PSD indicator, which I presented before, but just as a reminder, it's percent greater than 4.75 millimeters, so percent gravel. divided by the percent passing number 100 mesh. We also looked at percent clay. We looked at just percent passing 100 mesh. We looked at some of the Atterberg results. So we looked at correlating it to a number of different physical measurements. But what we found is that correlating it to the PSD indicator provided the best correlation, best relationship with an R squared of about 0.82 there, which we're seeing here in this graph. Now, what this graph here is, we have the saturated hydraulic conductivity on the y-axis, the PSD indicator on the x-axis increasing. So the benefit of this is, so if you're able to go out and easily acquire physical measurements, in this case, particle size distribution, calculate the PSD indicator, and then so for this particular ore, you could look at this yellow line right here is this 100x safety factor. So you want to be above that yellow line in the white zone. You can look at this. So at a PSD indicator of 4 or greater, then that would indicate, and this is by the way, this is just first lift conditions, what this correlation is. So measurements under first lift conditions, saying that the ore should be sufficiently permeable if the PSD indicator is 4 or greater, but below 4, you may have permeability issues under first lift conditions. So this work was done. What were the implications? How did Round Mountain use it? So what they were able to do is use this information. And I guess in addition to their operations information, because now they have a couple of years. By the time we completed this, or did this work and completed, they had a couple of years into operating the leach pad. But as well as our permeability test, they were able to do that to recalibrate their recovery model. And that's what's showing here. The graph is the monthly gold ounces recovered versus time. The blue bar chart is what was budgeted and are forecasted. The red was actual production, and you can see they were off the mark for the first couple of years. After recalibrating and incorporating the hydraulic measurement program into their analysis, they were able to better predict their recovery. Also, in addition to that, is this work allowed them to identify problem ores in advance. So as they're mining and they can now plan for where their problem ores and help them to optimize what the blending of that ore would be to maintain sufficient permeability. So in conclusion, with this work, I think it shows that a well-designed hydraulic property testing program can simulate conditions in an operational heap, at a large-scale heap, and going from a lab scale to a large-scale heap. And the data then can be used to evaluate ore permeability for different ore types, the optimum heap height and irrigation rate to minimize the effects of consolidation, and also the appropriate ore blending ratios to maintain permeability. And then also that physical property data can potentially be correlated to the permeability results to allow a relatively low cost and efficient method to predict ore performance in terms of permeability. That's all I have today. Thank you for your attention.
Oh, thanks for that talk. Is there any questions? If there are, please go to the microphone toward the center.
What were the particle size limits and heap stack height limits for the flex wall testing?
So typically in this particular one, 2 inches is the particle size limit. So for the 12-inch column, that was the maximum. And then the limits in terms of what we could test down to what would be equivalent to 80 feet depth within the leach pad.
Okay, and for the feeds that you're testing, are you just scalping off the oversized material, and then do you account for that in your those PSD correlations that you were taking?
Yeah, so sometimes what we do in this, and I think in this particular case, we won't necessarily scalp it. We'll take the greater than 2 inch and we'll break it down to be 2 inches, because at some point, yeah, I mean, with the larger, the gravel size particles, they're behaving, their impact in terms of the hydraulic performance of the ore. I mean, so that we can maintain that gravel component in there, but we'll break it down to be 2 inches to go in there now. But there are other cases where we would scalp it out and then we apply a correction based on that material that's been removed. Yeah.
With breaking the competent rock, are there any concerns that might actually improve the permeability by better distributing the competent rock through the feed?
Yeah, that's something we have to pay attention to. And there's actually, I mean, we have a certain threshold where we maybe would break that down. I mean, if we're seeing just based on the ore, the full particle size distribution of the ore, we make that decision whether we break it down to just have that we think it's better to have it all in there and break it down versus scalping it off the top. So you're right. We have to be aware of that when we're modifying the gravels like that, man.
Hi there.
Hi.
It was a good talk. Thanks for that. And just a question, it may be beyond the scope of your presentation, but you mentioned at the beginning that it went up to 50 feet high and that failed, the permeability got reduced. Then they reduced it to 25 feet. And I mean, that seems like a regressive approach instead of preemptive work that you did instead of doing that at the beginning. Any reasoning, explanation for that? Why this backward?
Yeah.
Against the, I mean, we in any case, heap leachers, many of them that we do, I've been involved, we suggest that, well, you do a permeability test under varying load, detailed analysis of that before you decide that. Any comment on that?
Yeah, unfortunately, because we weren't involved out there prior to this. So I'm not really sure the story behind that, but you're absolutely right. I mean, implementing a study like this in the beginning and the feasibility part is definitely would hopefully save you a headache in the long run.
I'll just ask a quick one if the man speak loudly. You spoke about modeling down to 60 feet below, so 3 for 4 lifts. You said it's possible up to 80. Is there a way you could manufacture the compaction test and you could simulate a depth like 200 or 300 feet?
Yeah, and I'll just repeat it for people who are online asking if there is a way to modify the testing apparatus, I guess, to be able to go to deeper depths beyond 80 feet. And, you know, for Mike Yao, who's here in the audience, who's our lab director, that's probably an answer that he would be better qualified to give. I mean, I know, and Mike, maybe I'm wrong here. One component with that is having that rubber bladder is you under at a certain pressure, you can puncture that bladder. So we have to be careful about that, particularly if you have gravels in there that have some sharp edges. And I think I'd probably need to get you meet up with Mike Yao and get a better answer than what I gave him.
Anything else? All right, well, thank you so much, Jason.
All right. Yeah.
And I think I can partially respond to the ore quality at Round Mountain. The initial samples that were available for testing weren't so clay as the actual production ore. So it was a little bit of a surprise for the geotechnical engineers that didn't see that clay stuff coming. So our next presenter is Guillermo Torres. He is a geotechnical specialist and consultant for Geotecnos in Chile. And Guillermo will be talking about the geotechnical evaluation of properties and liquefaction potential using CPTU for a heap and RUM leaching facilities. Guillermo.
Well, thank you very much. I'm very pleased to be here and presenting you what was our evaluation. And first of all, I would like to also acknowledge my colleagues that participated on doing this job. Sergio Pinos, which is our geotechnical consultant down in the company, and Mr. Ricardo Moffat, which is PhD in geotechnicals, who did all the modeling and the analysis for the interpretation of the results that were coming out of this investigation. Well, first of all, how did it came out is we've been performing over 8 years with a DCPT dynamic compenetration test evaluation over reviews, especially to evaluate bearing capacity for the equipment that was going over surface in terms of what would be safe for the operations. So taking the experience from this DCPT evaluation, which we could get into a depth of some 10 to 15 meters for the geotechnical evaluation and interpretations of geotechnical properties, we were retained to performed deeper analysis on a heap leach facility in northern Chile, which was up in the height of that moment to some over 210 feet in height, and evaluate what were the geotechnical properties of the heap, and also ROM facility that was placed by it. The main concerns were that these operations were long-term operations over 20 years since they first started. So the change of the geotechnical properties that could be encountered could be be facing some concerns related to potential dynamic liquefaction or static liquefaction, especially since the ore metrics change over times. Now they're processing material with lower ore grading. So there is a lot of other materials with different geotechnical properties that were being placed over the facility with more argillic content that had some concerns related to what if there would be in interleft development of some phreatic level that could be some concerns or some clogs that could be fine. So the technique of using the CPTU measurement has become or has been very practical usage, especially especially in the industry of the mines related to sands coming from the tailings operations. So this was kind of a first impulse to be improving what would be the results of applying this technique over ROM facility and over heap. So this first approach of this mine was very useful for other operations because the available space for going or constructing new facilities is being very restricted in terms of environmental, and also the heights of the facilities are growing and growing in time. So concerns as this that we evaluated in here are pretty much the concerns of much of the operations down in Chile, which is pretty much also seismic country. So the following presentation summarizes the work, the geotechnical work and assessments in fields, and what it was complementary with laboratory works that were done in some sampling. Well, the evaluation of the potential liquefaction in terms of safety factor was using the cyclic resisting ratio, and which was evaluating coming out of the proposal. It was evaluated against what was the cyclic shear resistance evaluated directly from the CPTU, gathering information from the heap leach facility. So the factor of safety was generally determined by the cyclic resisting ratio by the cyclic shear resistance ratio. The method was applied using the proposals of Bolton and Idrissi. And well, it is a systematic and a modeling that approaches the measurements directly from the CPTU. So in terms of you can calculate directly what would be the cyclic resistance ratio and the cyclic shear resistance from the readings. So the field works were performed over the surface and the selected points for measurements around the perimeter of the of this ledge facility. Here is the heap facility, and the round facility was placed over here by very close to the pit. So 19 points were selected over the heap facility, and 22 points were selected over the round facility. The desired depth at which the drillings were to get, it was to 25 to 30 meters in depth, which is close to, we'll multiply it by 3, so it will be 75 or 90 feet in depth. Well, in addition, we performed complementary studies, doing some down the hole tests. And also we did some dissipation test every 5 meters in all of the testing boreholes. Basically, what we wanted to do is to get a better approach of as much as information as was possible to correlate the information that was being gathered from the CPTU and the interpretations that could be coming out of the direct readings and correlated with lab tests, especially in terms of what would be the saturation of the moisture contents of some samples, and see if it was close to or what was the saturation ratio, and see if it could come out with some problems or some issues that could rise up the red light in terms of static liquefaction. So here are some reading outs of typical CPTU, the readings. As you can see, it was very straightforward, and there are some points and gaps that were here at the 40 meter depth to 20 meter depth. There were some points that couldn't be addressed with more detail, which was later more evaluated also with the samples that were coming out of those. Here are the shear weights that were measured from the downholes. And here also were some of the points that were written out from the dissipation tests that were carried out, and also those results were compared with the samples that were taken out to lab for some geotechnical basic evaluations such as gradings and moisture content, which was one of the focuses that we were facing on. Well, here you can see some samples taken out from the heap leachings at some depths. And this was to calibrate the stratific interpretation that was obtained, and this sample was included to demand the USES classification, and to calibrate what was the interpretation expected and what was expected from the operation in terms of what the operators were aware, where were the points that would be of their more concerns in terms of higher potential of failure or more aim to be liquefied in terms of static or dynamic liquefaction. So for the interpretation of the stratigraphic, it was used the Robertson proposed graphs using the basic parameters obtained from the CPTU. And well, it came out, sorry. It came out very close to what it was expected, especially in the heap which was sand and lime sands in the top, and with more sandies going on the ground. The first 4 meters were pretty much fresh materials being leached, and in the as we were going down, we were encountering some interlifts of more alkalic concentrations and more sandy concentrations at different depths, which you can see as in here and as in here. In one, this is one of the general interpretations, but the material that it was interpreted was pretty much as it was expected. Well, and which was also as an expectation after this analysis was to obtain all geotechnical parameters to perform further stability analysis. So it was first do a general evaluation in terms of if it could be foreseen any concerns related to dynamic liquefaction or static liquefaction. And after that, which was read out straight from the analysis of the CPTUs and the analysis of the gathered data. And after that, with all the interpretations of the geotechnical parameters, all this was taken out to perform analysis for slope stability and deformation analysis further. So as you can see here, it is a general table where you can see the shear resistance and relative densities and friction angles and cohesion, which was further taken for the analysis of stability and deformation. So for the liquefaction analysis, the parameters were taken out and it was performed using different magnitudes of seismic, using general ground acceleration as 0.3, 0.4, 0.5. Now, at this point, it is important to take into account that it was assumed that for the evaluation, a very conservative assumption, which was that the material was 100% saturated. So this is the results related to what would be the concerns in liquefaction evaluation had to be taken that into account for further interpretation. Just as a reminder, as Chile is a very seismic country, the seismic parameters were taken from the seismic charts that were close to the site, and it was taken out the highest that it was expected for or could be striking the heap leach facilities at the mine site where it was located. This investigation. So this is the result of the analysis for the 0.3 ground acceleration, general ground acceleration, and here in the middle one, in the red area, there's the highest risk. So at some points there are a few points that are passing over here in the concerned area. And if we take into the diff, we can see here that the first meters are probably the ones that are with higher concern of dynamic liquefaction or static liquefaction. Well, dynamic in this case. Here we can see the result for 0.4 general ground acceleration. And the concerns here are even down to 11 meters. I mean, 7.8 meters in depth. And 0.5, we get down to 8-9 meters depth, which was the depth of concerns of potential of liquefaction, dynamic liquefaction. So in summary, liquefaction analysis in the heap, that there is a record of liquefaction down to 15 to 25 meters in the within the heap. This was taken into account also what were the results in general and the interpretations of what was the material being found out, and also what was the saturation level that it was found from the lab testings. Oops, sorry. I want to show you this. Yes, this is the general information gathered from the lab testings from the samples, and the saturation percentage that found out in some samples, in just one of them went over the 80% that it could be some. It is a general assumption that over 80% it could be suitable for static liquefaction. So in this case, all samples were much below the 80%. So the concerns related to static liquefaction, even if it is not totally eliminated, it is still very low. Well, the result shows, or it summarizes, the maximum saturation was found of 86%. One of the samples just overpassed the 80%. Well, we did the same performance over the ROM facilities, and in ROM facility, they were considered to perform 22 points that were also aiming to gain up down to 25 to 30 meters in depth. But related to the grain size or the blockies that could be found along the path of the CPTU, the depth that we could get in general in average was 15 meters. So it was half of what we were aiming to get. Just as for the record, in the heap, all the tests of the CPTU test got down to the expected depth. So there were not concerns in terms of the materials for being the performance of the test. But in the ROM facility, there were even in some cases, we encounter blockage due to the size of the material that was on the pathway. So in this case, in average, we got into 15 meters, but there were 2 out of the 22 tests performed that had to be eliminated because it just got down to 5.5 meters, would be 15 feet, and another one got to 9 meters in depth, which is 27 feet, which is what it is a low percentage of all the performed tests. It is, but when the conclusion was that when you are performing the CPTU test of the ROM, you should take a deeper look in what is the geotechnical expectation of the material that you're going to be encountered, because all that is related to the performance of the tests and the movement into place, it is something that needs to be considered. So it's not totally discarded, but it needs a better understanding, and it needs further information from the geotechnical operations. Well, in this case, as a conclusion, it is used that the tested areas of the piece of the heap consisted mostly in silty surface, which was in terms of the characteristics of the material, turned out to be pretty much as it was expected from the heap. Well, and there was also a correlation taken from the piezometers that were placed within the heap, and taking into all the samples, taking into account the samples that were taken to lab for saturation test or moisture content. For this material in particular, there's no higher concerns in terms of liquefaction, in static liquefaction or dynamic liquefaction. Now, it needs to be taken into account that this is a photograph of the moment that it was evaluated. So if there's as a general recommendation in terms of the operation changes in time, you should be, it would be recommended to consider an investigation like this being performed every such periods. And well, in general terms, as I was mentioning for the ROM facility, the difficulties encountered for that do not totally discard the application of the ROM facility, but it is highly recommended to take a deep look into what is the expectation of the material. So all the effort for the performing the CPTU will not be dismissed in terms of there is a high possibility, especially if you're finding a lot of blockages during the performing of the test. Finally, you will not encounter or could be not gather as much information as you wish. So this was it. Thank you very much.
Any questions for Guillermo?
Okay.
Well done. Thank you.
Thank you.
All right, our final talk of the session is by Ville Heikkinen. Sorry. Should have a do-over on that one. Ville is the research manager at the Terraframe Sotkama mine in Finland, and he will be speaking to us on a talk titled Process Update on Dynamic Heap Bioleaching of Black Schist Ore. Ville.
Okay, thank you, Brian. It's nice to be here. Never been to US, so it's a nice experience for me. Yeah, I'm going to tell you about Terrafame, some process update. And I think 6 years ago, Antti Arpalahti was giving a presentation about our process in this conference in Peru. Okay. And first, some figures about Terrafame, last year's numbers and so on. Then our production process briefly through, focusing on process development for recent years. Then some future ideas about our recent investment and future plans. If we have time, we can go through some financial numbers from last years. just picture of our primary heap in this. Okay, here are some numbers. So last year, our sales was about 378 million euros. These are in euros, but just quite close to dollars also. And you can see the ramp up of the battery chemicals plant, just 27 million, but this year going much higher. Yeah, at the moment we have about 900 employees and also quite the same number of partner companies. So it's quite big amount of people there. Last year's figures for the production, nickel 28,000 tons and zinc 54. So we are quite close of our original target of 30,000 tons of nickel per year. Also, you can see the capacity of the battery chemicals plant here, but of course, ramp up is ongoing. So figures are still quite low. Yeah, so the process itself, we start with the open pit mine, then bringing the ore to materials handling, crushing in 4 stages and agglomeration, stacking, heap leaching pile heaps in primary and secondary phases, taking the pregnant leaching solution to metal extraction, sulfide precipitation, and in the end we have this battery chemicals plant SX process. Okay. Back. Here we have picture of our area. So mine, and there's 3 kilometers distance from the open pit to our factory area where we have materials handling, leaching heaps, metals recovery plant, and battery chemicals plant. Also, already ready-made uranium extraction plant is seen here. Yeah, some details of the process. Here. So the mineral resources, we are updating them every now and then, and last one is from 2018, and we have about 1.5 billion tons of resources, and as a quite low grade ore, nickel content 0.25% is counting for about 4 million tons of nickel totally. Okay, then more detailed for the mineralogy. We have gangue about 50 to 85%. graphite, about 10%. Sulfides is where the valuables are, depending, varying from 10 to 25%. And in the sulfides, we have pyrrhotite, pyrite, and other just taking them here. Other sulfides, which in which nickel content you can see here. So most of the nickel is in pentlandite, but also in pyrrhotite we have significant amount of nickel. And in the northern hemisphere where we are, the pyrrhotite is the key issue to have the process ongoing through the winter. So we get the heat from the pyrrhotite and alapandite oxidation. Yeah, focusing on our heap leaching. So solution circulation, pregnant leach solution cycle. Here, starting, let's say, metals recovery plant, we have solution coming and pumped through to secondary leaching without, we have taken out the valuables. Okay, no. So we have in secondary we have 4 heaps and the circulation is trying to build up the solution concentrations as much as possible. So circulating in the secondary, then pumped to primary irrigation through the heaps to PLS ponds and then fed to metals recovery plant. Of course, this is the, let's say, smaller circulation, and we have so-called bigger circulation in both primary and secondary heaps, which is about, but let's say this is 10% of the irrigation circulations in the heaps. Yes, here we can see situation in the winter. We have yearly about 5 months period of temperatures below 0 degrees Celsius. And of course, although the heap is quite warm, inside temperatures about 80 degrees Celsius, and there's no major buildup of snow on top of the heap, but still some piping and smaller pipes tend to freeze if solution is stopped. So it's a little bit struggle or during the winters, but the main process is ongoing just nicely. Yes, then some developments what we have done to improve our process lately. Yeah, in the original plan, we had residence time in primary about 18 months. And we have seen that the primary leaching is continuing quite well after that. And we are expanding our primary leaching. We have taken first step with 150-meter extension for 2 primary heaps, and we are planning to have totally 600 meters in some years, so that we would have additionally 1 month more time in primary. We have also increased our heap height, taking more tonnage to the primary leaching. Originally, we have 8-meter heap height, and nowadays height is about 9.5 to 10 meters. That's the maximum capacity of our stacking equipment. And when we increased the height, we saw that we need more air, and of course, for the reaction itself, air is very, very important. And we have also increased the capacity of our blowers up to 100% of the original capacity, and also made some assembly changes. And nowadays we are assembling aeration pipeline inside the heap in 3 layers, which hopefully gives us a better distribution for the air. Yes, and in secondary leaching, we have a situation that as it is a multi-lift heap, and we have permitting certain height for that, and the height will be achieved or coming to end, let's say, in few years, and we need new area, new secondary leaching area, and that's quite big investment coming in a few years, and starting into 2026. And that also will be quite close to the present one. Yeah, in the secondary, as we have heard some presentation about this stability issues, we have seen that in the multi-lift process, the risk is always there, and we have monitoring program to see how the multi-lift heap is performing, and we try to see the possible issues, stability issues beforehand with this. And we use this INSAR technique. In this, we haven't seen any bigger movements, and you can see red dots here are marks of movement, and they are we can see that they are the present progress movements, and we don't need to worry about them. As we all have our challenges, gypsum precipitation is the one for us. With the calcium bearing minerals leaching and sulfuric acid, we see gypsum precipitation in our pipeline quite heavily. Quite heavy maintenance is needed for that, but for the moment we are surviving quite nice. We will address some effort in the future for this. The water balance has also been an issue a few years ago, and it is always a challenge, changing that challenge for us. So we are in a net positive precipitation area. We have years of negative, but some years of positive, and that gives us some challenges, and we are using purification, separate purification for extra waters on those years. This year seems to be quite dry, and we are quite easily managing with our waters. Okay, we have learned our lesson with this, and water management is nowadays quite very well organized, and no challenges, bigger challenges with the water balance anymore. Okay, then this battery chemicals plant is our most recent investment, and ramp up is ongoing. And we can see every day better results, and process is working there. Raw material comes from the nickel sulfide precipitation, so it's on material, but we have also possibility to take raw materials outside, but that, of course, that needs some permitting before. Yeah, for this kind of heap leaching operation, we know that the carbon footprint is low, and we are very proud of these kind of numbers. It is very important for the battery chemicals market also that we can show them our carbon footprint as low as it is. Yeah, maybe some final numbers in the end. History of nickel production leading nowadays quite close to 30,000 tons, and this year we will exceed that. Nickel tonnage is giving us about 400 million sales per year, and some investments, and next one will be the secondary area. Okay, thank you.
Yeah, thank you. Is there any questions?
Yes, I have a quick one. Could you please talk more on how you install those aeration pipes? Thank you.
Sorry, the
Could you describe a little more in detail how you install those aeration pipes? In the
aeration pipes, okay, yeah. Maybe I'll take back to the picture where we have those. Yeah, we have primary stacker stacking the heap, backward filling, and with that so when the stacker is stacking the primary heap, we have we make shelves to the heap and assembly the pipeline there in 3 layers, and then it's buried with the next layer. So it's handmade assembly. Yeah.
Looks like no more questions. So with that, we'll end this session. There's lunch next door and then a panel discussion after that. And look forward to seeing you out there. Thank you again.
Thank you.